5.3 The extremal path method for evaluating the connection. Coefficients. A geodesic is a parametrized curve that extremizes the integral. See equation 5-14. Using affine parametrization. Variation leads to the geodesic equation. See equation 5-15, where the normal gamma s are the connection coefficients needed in the G sub L calculation. See equation 5-16.
Let's start with path integral to be extremized. See equation 5-17. So, see the equation shown. Consider equation 1. See the equations. N to the RTH power term leads to coupled geodesic equations as there are d squared t over d lambda squared wedge d squared r over d lambda squared terms in the above. Calculation of delta I sub are needed next.
See the equation. Consider equation 2. See the group of equations shown. Equations 1 and 2 are grouped to have no d squared r over d lambda squared term. See the equations. Relating to the form, see the equation. We get
see equation 5-18. See equation 5-19. See equation 5-20. See equation 5-21. If n to the RTH power equals 0 and there is no t dependence, d operation yields 0, then only normal gamma sub RT to the TTH power above is non-zero with n prime n to the -1 power. This agrees with the previous calc.
Now to group with no d squared t over d lambda squared term. See the group of equations shown. Thus, see the group of equations shown. Thus, see equation 5-22. See equation 5-23. See equation 5-24.
See equation 5-25. These also agree with results for n to the RTH power equals 0 and no t dependence. Now consider. See the equations. Thus, see the equation shown. And the coefficients are. See equation 5-26.
See equation 5-27. See equation 5-28. For the phi of lambda variation, see the next equation. And the coefficients are. See equation 5-29. Let's apply the geodesic method to BH spacetimes in coordinates that cross the horizon. Kruskal coordinates. The Kruskal coordinates are used to arrive at an action.
See the equation. See equation 5-30. The geodesics are variational minimal of the distance measures. Between events, we consider here only converse spaces. Using affine parametrization, extremizing. See equation 5-31. Is known to yield x double dot to the mu th power plus normal gamma sub alpha beta to the mu th power x dot to the alpha th power x dot to the beta th power equals 0. Where normal gamma sub alpha beta to the mu th power s are the needed connection coefficients.
Proof that carries of extremal length are geodesics on page 316 MTW. Discussion given in box 13.3 of MTW of how a geometric principle of extremal length may be replaced by a dynamic extremal principle based on the simplest chord. INV equalization of 1/2 x dot squared, i.e. 1/2 g sub mu v of dx to the mu th power over d lambda, the fraction with numerator normal dx to the vth power and denominator d lambda, which in the form. See the equation shown. With affine parameter, yields the equation x double dot to the mu th power plus normal gamma sub alpha beta to the mu th power x dot to the alpha th power x dot to the beta th power equals 0. Geodesic Lagrangian method for calculation of the connection coefficient is then done. See equation 5-32.
See equation 5-33. See equation 5-34. Vary v of lambda first. See the equations. See equation 5-35. See equation 5-36. Vary u of lambda to get. See the equation. See equation 5-37.
See equation 5-38. Vary theta of lambda to get. See the equation shown. See equation 5-39. See equation 5-40. Vary phi of lambda to get. See the next equation. See equation 5-41.
See equation 5-42. The normal gamma prime sub s have been verified on the computer and see equation 5-43. See equation 5-44. In a coord system. Now let's compute G. We have see equation 5-45.
See equation 5-46. See the equation. So, see the equation shown. See equation 5-47. Where? See the next equation. So, see equation 5-48. Thus, see the equations. Thus, see equation 5-49.
Novikov. R raised to the asterisk equals 0 observer in Novikov. See the equations. Analysis of radial geodesic motion. See the group of equations shown. See equation 5-50. Consider radial motion. See the group of equations shown.
Then this expression would be in a Lagrangian, ready to be quantized. See equation 5-51. Alternate derivation of radial dynamical equation. See the equations. And since, see the next equation. Also, see the equation. So, see the group of equations shown.
Thus, see equation 5-52. Note about comparison with prior deviation, their Schwarzschild. Coordinates are used which break down at r equals 2m. However, if e goes to 0 as r goes to 2m, the result is also clear there too. So, partial derivative of theta with respect to tau squared minus 2m over theta equals -1, when theta dot equals theta theta equals 2m. Comparing with the usual Coulomb system in 1D. See equation 5-53.
See equation 5-54. See equation 5-55. See equation 5-56. See equation 5-57. See the next equation. Partial derivative of r with respect to t squared minus 2m over r equals -1.
Which is exactly like the throat dynamics. So, there is a direct relationship to a Coulomb system. However, instead of 0 is less than r is less than infinity, we have 0 is less than theta is less than 2m.